Hey, John here. So last time we talked about a general idea to design a direct map cache that could hold 256 slots of SD card blocks, which are the same in this design as a CPM track. So where are we going to store that? We're going to store it in the unused memory banks on the Z80 Retro board. Okay, so a quick recap here. Remember that the high half of the memory on the retro board is always pegged to bank number 15 because the design includes this U13A. This chip does only one thing. It has 4 OR gates on it like this. Whenever A15 is a 1, the machine is accessing the high half of memory. If this is a 1, these are OR gates. The outputs here will all be 1s. Therefore, this 4-bit value is 15. Hexadecimal F, which selects the topmost bank of the 16 banks in our SRAM. Whenever the Z80 is accessing the bottom half of the RAM range, A15 will be 0, and 0 ORed with some value X is always equal to that some value X. So whenever we're in the bottom half of the memory, whatever comes out of the low bank address bits propagates through these gates, okay? Side note, if you decide to use this for some other purpose, or it doesn't matter to me, even if you want to run CPM on it, but you don't want to switch around the bottom bank while keeping the top banks pinned to bank number 15, well, you can just replace this HC32 with an HC08. Done. Okay? Same exact design and everything. Since this chip only has 4 gates on it, and it only does this one function, if these are AND gates, which is what an HC08 is. It's a 2-input AND gate. It's just AND, not NAND, right? That would be an HC00. But no, an HC08, whenever A15 would be 0, if this was AND, then X ANDed with 0 would equal 0. So this would essentially flip it around the other way. That would pin the bottom half of the RAM to the bank 0 all the time, and whenever the Z80 accessed the top half of the memory, A15 would be a 1, and if these are AND gates, what happens is 1 ANDed with X, in this case, equals X, so the bank would then be whatever you specify. So the same exact design in every way, shape, or form, just switch out this one chip if you want to bank select the top half of the memory instead of the bottom. Okay, so where were we? We have this permanently tied to bank 15. And then the bottom half of the memory can be mapped into whatever RAM bank we want, including 15, although doing so seems kind of foolish. So anyway, as I mentioned before, I think the code will be simplified by a couple of instructions, granted, but still simplified if I did not choose to use bank 0 for the default where the TPA and the bottom RAM page goes and stuff like that over here. I should have probably chose bank 14 for that. Now, as I mentioned last time, it doesn't make any difference which banks I use for what purpose other than this one here, because it's hardwired due to those OR gates we were just talking about. Okay. Now, the reason I don't want to use bank 0 down here is because the math for a direct map cache, and just about any cache, works out really nice, provided that the memory and the slots and all that start out at an address that's equal to a power of 2 and whose size is equal to a power of 2. And if it's banked, every one of the banks should be a power of 2. Therefore, by putting this here, this is the really bad place to start our first bank of all of our slots, right? So, and because it doesn't matter what I use for this one, I'm going to make that one map over to bank 14. Therefore, leaving bank 0 to 13 free for whatever we want to do. Now, let's see what I did to the code since last time we were looking at this. I'm in the CPM Retro directory where my BIOS is. And when you compile it, it regenerates the CPM image and corrects the errors and stuff. I talked about that long ago, and creates temporary files and stuff in here. So I just did a make clean. This is what we're starting with in a new build, okay? So this is the BIOS, talking about that for a half a year. I removed from this file all the SD reading and writing code. The whopping 2 functions that do that, okay? I've moved them down into these files down here. And the reason I decided to do this is because in the retro file, what happened was the code was starting to get a little bit messy. As you recall, the first draft of our BIOS, when we stubbed in the reading and writing routines, which is now moved down to here, I had this code logic that allowed us to fake the disk and not even care about the SD card at all, just to make sure the BIOS was working. And I always returned what appeared to CP/M to be a blank sector, and if it ever tried to write something, it would throw it away and return an error. Okay? So what I did is I took that code out of the BIOS and I just put it in this file here. I then took the code that we've been using for the last half a year and put it in the no cache file down here. The new code I'm going to write is going to go in here. The idea is now inside the retro ASM file with the rest of the BIOS, I can just include whatever one of these I want. Otherwise, we have all this conditional if, what version do I want, and all that. It got ugly, okay? So I just factored all that out. Let's look and see what's going on in here. What else did I do? I added this little memory map here, some doc in here. So this, I don't know, maybe this probably should be put into my, also factored into those other files to show me which banks are used for the cache. But for now, I'm going to leave it here as we work on this, okay? So what do I do? The big change is I moved the CP/M 0 page in the TPA. I'm going to run it on a bank 14 instead of 0, okay? I'm going to formalize that by creating a symbol called low bank, and I'm going to set it to E so that if I need to use it anywhere else in the BIOS, I have a name instead of this hexadecimal E floating around, this disembodied number that has no meaning otherwise, right? Quick recap. Remember, the flash loads in 16K from the beginning of the partition, what looks like a floppy disk, into memory starting at load base, which is a constant defined in memory ASM, to equal C000, which is basically, 16K. It's the last 16K of RAM. When the flash is done loading it, it branches to the address at load base, starts executing, it runs into this jump instruction, which takes it down to this BIOS boot routine, which is the cold boot logic right here. What this is going to do, I added a whopping line of code right here. Instead of selecting bank 0 and then proceeding, it's going to select bank 14 by doing this. Now remember, the value that selects the bank is written into a latch. This latch is used by the printer as well as the SD card as well. And we'll see that this is, in order to save money and simplify the hardware, this is going to kind of make our jobs a little more difficult when we're writing the software. It's going to limit our options in certain circumstances, okay? But for right now, what we care about is these 4 bits that specify what the bank is that's supposed to be mapped into the bottom half of RAM is in the topmost 4 bits of the value written into this latch. So that's why I take the low bank number and I shift it left 4 bits, okay, and OR it in with all the values and stuff that I used to initialize all the other bits in that latch. I stored it in this variable so that we know what it is, because that latch cannot be read back, which is another minor nuisance of this simplistic design. We need to remember what it is sometimes, so I have to cache it somewhere. That's okay. I have a 1 byte storage area for that. Then, of course, I output it. After this, there's almost no changes to the rest of this BIOS. Let's look at the few changes that are in here. If we scroll down, eventually this calls, there it is, there's a new call, RW init. This used to, if you recall, have 2 instructions that set a variable equal to 1 to invalidate the SD card 1 block buffer cache that we've been using for the last half a year. But now, since I factored all the code out that does the reading and the writing, this code doesn't know what it's supposed to do. So this function here was added to those 3 new files. You have to have the BIOS read, a BIOS write, and an RW init function. Then we'll see what that gets used for in a minute. This is called in the hard boot routine that we're looking at right here, and it's also called in the warm boot routine somewhere. Here it is down here, okay? So this is the main changes to the BIOS so far. If we go to the bottom of this file, the buffer, the SD card buffer used to be in this hole here. Obviously, we don't need it unless we're using that one version of the read and write routine. So that got factored out into the read and write file for the one block buffer code. And up here where the read and write routines used to be, we have this. Okay, so we either include the original stub, or you can include the no cache, which is what we've been using for the last half year. That's the one block buffer to deblock and block the access to the SD card. And here's the new one. Okay, and the new one, I'm starting out by just making a copy of what we've been using the whole time, so I can start hacking it up. And basically what I want to do is I want to use the approach that I'm going to kind of still have the current code in place while I sort of stub in a bunch of debug code to check to make sure I got all the right values for the various values, like which slot number I'm supposed to be using when I get a certain track, and I'm calculating the right value to put into the memory bank latch and stuff like that. It's super critical that we just run this thing to death and print out all these values and verify that all of our code and math is right before we actually try to run it. Because debugging this without an actual debugger and a single stepper and all the fun, lazy tools that we can use today, we don't have any of that. So it's absolutely critical that we don't make any mistakes. Because if you take the memory out while the thing is running, that's just a nightmare to debug. I don't want to deal with that. The only way I know to do that, by the way, is to start connecting up oscilloscopes or logic analyzers. And if you watch my channel, you know my logic analyzer is broken. So this is going to be real hard to debug without a logic analyzer. And all I have is a 2-trace storage scope in a 4-trace traditional analog scope. So I don't want to make any mistakes. Real conservative here. Debug this thing like crazy. Okay? So let's look at these files. Here's the stub. We saw this maybe a year ago at this point. Wow. Okay, so each one of these files now, because they're totally self-contained, they have their own debug flags. So these can be as noisy or as not, and we're going to be fine. You know, it won't affect the other BIOS code or any other libraries or anything else like that. I probably should have done this a year ago, I confess. But this is how all code grows, right? It grows until you go, oh, God, I need to refactor this. And you make with the refactoring. So that took place last night. Okay, great. Here's the read routine for the stub. You'll notice this does not have a dot in front of it anymore. It's because this is in a different file than the BIOS. Therefore, it has to be a global variable instead of a local one now. Okay? And this I discussed long ago. As long as you return all E5s in all cases in CPM, it will think the disk is 100% blank and there are no files or anything else. And CPM itself will work fine. It's happy with that. That's why I chose to do this. So this is my stubbed in the null, no-op kind of read routine. The write routine is some debugging again, so we can see what the CPM wants to do, followed by, I have an error. You can't write to me. So I have a read-only blank disk. And here's our init routine. In this case, there's nothing to initialize, but since this was a weird wonky test case, if I ever have it enabled and I build with it, and I boot it up, at least it'll print this out to kind of remind me. By the way, you're running with the stub library installed here, so don't get confused when there's no files on your disk, sort of thing. All right, so you can see where we're going with this now, right? So here's the no cache. All this code is the same as it used to be. I moved this equate out of the middle of the code, so it's a little more prominent, kind of remind us all that, I still haven't done the simple math routines that are needed to provide a self-configuring mechanism for SD cards that are partitioned in any way other than the way I told you to do it if you're going to build yourself a retro board. And what I told you is to put your partition so that it starts exactly on block number hex 800 on your SD card. Okay, and the reason for that is because I hard-coded it right here, and I don't have a way in this code yet for it to read the partition table like I do in the Flash boot code, to find where the partitions start, and then use that as the basis for this value here. We'll work on that at some other point. Right now, I want to get the cache to work. So this is a no change. I just moved it to be more prominent. That's all. Again, the global read routine followed by the exact same code we have before, and a global write routine followed by the exact same code we had before. And then down here should be our buffer. Okay, the buffer cache for the single block code is here instead of in the main retro code. And I moved it in here in case that's not obvious yet, because it's only used if this version of the read and write routines are used in our BIOS. Otherwise, it's not used at all. Don't waste a half a K of RAM when you can't afford to do so if it's not going to get used, right? Now, the init routine here gets a little noisy, and it's the one that is normally used, at least for me. I don't want to print this out, so I comment this noise out, but it's the same kind of a thing. And here's where I invalidate this buffer here, the valid flag. I set it to 1, and it marks it as empty and unused. Okay, that's critically important. Otherwise, you could get garbage data into your the BDOS will get really confused if you start giving it garbage when it wants to read its directory and stuff like that. All right, so here's the new code. All right, so step number 1. As you see, it starts the same. I've got a couple of subroutines up here. This stands for direct map track to slot. CPM track number to cache slot number. Okay, that's what that stands for there. This one is direct map slot number to bank. Right? Because as you recall, we need to be able to get the slot number from the CPM track, which is brain dead simple. We just throw away everything but the least significant 8 bits. This is most of what makes a direct map cache directly mapped. You don't have to do anything fancy to do this. And you also don't have to do much that's fancy to do this either. Okay? We're taking the bits as they are. We're taking them out of the value, and we're using some of them, but not all of them, to directly determine the values that we want. As you can see, this is the crux of the whole cache logic right here. Ooh, that's hard. This is why we use direct map caches. Okay, you'll see this is much easier than a fully associative or a n-way set associative cache. These routines get more complicated in those cases. However, there's a reason to use the more complicated code in here in the future when we look at fancier versions. It's because you'll find out that those caches can be more efficient. This one's super simple to do, but it may not work as well as we'd like it to, right? So the cost is, if the code's super easy, it may be a little bit wasteful. We might not get an optimal situation out of it. If we complicate this, that's the tax we pay to improve the efficiency of how many slots and stuff map into our cache. We make better use of our resources if we think and work harder at trying to do so. That, I guess, is what I should say there. The direct map is the easiest way to do it, but it might be wasteful. Okay? All right. So it doesn't get easier than that. And it pretty much doesn't get easier than this either. As we mentioned before, in order to get the block number from the slot, we extract 2 of the bits from the block number, which comes in the HL register pair, okay? But in this particular code, H must be 0, because, like I said before, the slot number, by definition, is the bottom 8 bits. So while I formally suggest that HL holds the slot number, by definition, when there's only 256 slots, H must be 0. So I'm only going to mess with L and don't care about the rest. I'm going to shift it 2 bits to the right, and these are the patterns we looked at last time. And what we get is the block number is sitting way over here on the left, followed by some stuff we don't care about in this context. We're going to shift it right again. And this is a rotate instruction, but doesn't matter. When we're done with that, we're going to end it with a hex 30, which is going to force all these bits over here to be zeros, leaving us with this 2-bit number there, which we can then directly store into our latch for the value of these bits here. And of course, if and when we ever do that, we need to make sure that we don't accidentally twiddle these values down here. And that's why we saved earlier on in the BIOS the value that's in this latch. Every time we update it, we need to make sure that we don't accidentally change the other bits. So if I'm going to change the bank number, I want to say, and don't change these. So I have to go get the current value and combine it with the new bank number and store that into the latch, right? Okay, so that's what this one does. What does this one do? This is slot to address. Talked about this one as well last time. Given a slot number in HL, again, H must be 0. So we only care about the L. We stick it in the accumulator and we get the same thing we did before, slot number, slot number. But what happens is in this context, we don't care about the bits that will turn into the bank, okay? So we need to get rid of those, and we need to align the rest of these bits to where they need to go to define our address. So to do that, we need to move it to the left 1 bit. So we have garbage followed by these 6 bits followed by garbage. We then do an AND with a hex 7E. We get 0 followed by the 6 bits followed by a 0. And that's in the accumulator. We put the accumulator into H, put 0 into L, and now we have the exact bit pattern I talked about last time that says, given a slot number, if the bank of memory is mapped into the low half of the address range, what would the address be of the data in that slot? And that's what we get from right here. That's how we do this. Again, it's directly mapped because we don't have to worry about translating these AAAAA values. You might argue I am, but I'm not. All I've done is I've taken the 6 bits and extracted them out, and I'm going to use them as they are in a different context. Okay, and that context is I need those 6 bits to be right here. Okay, a fancier cache, we might be twiddling all these AAA bits and relocating them and other such things. Okay, but that's what makes this a direct map cache. Okay, so what am I going to do? I said I copied the no cache code, and then I added this right here. Okay, so what am I doing? I'm going to call those routines, and I'm not going to do anything with the data other than print it out and make sure it's right before I start dorking with my memory, because the whole house of cards comes down if I blow it. All right, so what am I going to do? I'm going to print out, hey, okay, first of all, let's remember this is the read routine with the usual debugging. We've seen this lots before. It says, hi, I'm the read routine, and here's all the values that the BDOS set that describe which disk I want to use, which track number, what sector number, what the DMA address is going to be. This dumps all that out, okay? Then, rather than doing the I/O, I'm going to print out some more messages. I'm going to say, hey, I'm the direct map cache guy now. And the slot number is, and I'm going to go get it, the code that we just looked at, and then I'm going to print out that slot number. And this is a little gratuitous since we know that all the slots have, 0 in the high half here. But as this evolves, we do more fancy caches. The slot, I'm going to treat it as a 16-bit value, even though you and I know that this is the only part that really matters. It'll always be 00 something, okay? Then it's going to say what? Given that slot number, what's the bank? Okay, I'm going to go back and get the slot, convert the slot to the bank. And these functions I specifically wrote so that you can call them back to back like this, and there's really nothing to do. What's returned from here is in the HL register, which is the input to this function here, which returns its value in the accumulator, and I just dump it out right there. Okay, these are designed to go together that simply. Okay, then I'm going to say, what do I, and what is the address? We were just talking about that. So given the slot number, again, give me the slot number, convert the slot to the memory address, assuming, of course, that the right bank had been mapped up up here into that latch, for example, which I don't do. Remember, I'm just printing this stuff out right now just to see what it would do if I actually used this data for anything other than printing, okay? So then I print out the address, I print a carriage return, a line feed, and then I fall into same code we've been looking at all before. In this code, this is actually the original BIOS code that still has the if then else's with there's the stub code and there's the one block deblocking. You could call that a one slot cache routine that we've been using for a half a year, right? So this is all the original code still all sitting in here. So, and I leave it all in here because I want to make sure that even though I'm just debugging right now, I want to still have disk routines in here that still work so that I can, exercise my debug logic. Now, the write routine, I've put this error routine in there. It prints out the debug, okay, and immediately says, I'm a read-only disk, error. And none of this code down here is even used. I can put an if zero down there, I suppose, but it doesn't matter as long as it fits. It's this vestigial inert stuff sitting down here, wasting space. The reason I do this is I'm probably going to make mistakes, all right? And I don't want it to get real confusing by writing garbage over the disk and then trying to figure out why I'm reading garbage back from the disk while we're testing, okay? So, newsflash, first draft, don't write anything to the SD card. I'm not that concerned about corrupting the SD card because we just recreate it all the time anyway. I just don't want to confuse myself when I'm running my little test routines and running test programs, if something should try to reach out and touch the disk in some way. I don't want to have to write all of the code before I can test any of it. So the write routine will always return an error, okay? Now down here below the write routine, we still have, because I made a copy of it, all the usual regular old single block SD buffer in there, and the same init code. And this time I also have a notice in here that says, oh, by the way, you're running the DM cache version. So I can, when I boot it, I know I'm running the right one. Okay? So let's run this and see what happens. First of all, does it build? Yes. Second of all, I've been doing all this yammering on. I don't remember if I have the right one enabled in the comments here. Yes, I do. I'm looking at the dmcache.asm file. Now, let's burn an SD card. And as I've talked about before, if you're on a Raspberry Pi, I have a make burn rule in here that you can then just run, put your SD card in an adapter, stick it in your Pi, do the burn, take out the card, put it in your Retro, hit reset. Let's see what happens. Okay, we got a lot of spew here because we have the debugging turned on. So let's scroll back to the top of the spew. Whoa, what's going on up there? We can figure out where this thing starts. We've actually seen this before. We got debugging turned on. Should print something about there it is. We're in the DM cache library. So piled right to the right thing. Now, we saw this once before. When you boot up CPM or you do a warm boot, what happens is the BDOS reads every sector that comprise the directory. And it builds that allocation, vector table to figure out which tracks are available and sectors and stuff like that, right? So what we're doing is we're seeing it all do that right now. So the first thing it's going to do is read track 20, sector 0. And I went through this once before, but let's, if you don't know what this is, back up and look at the early read routines and stuff like that, and the SD card videos and stuff like that, if you want to get re-caught back up. But the short of it is, it's going to read in 16K because that's what the disk parameter block says for this particular file system is the size of my directory. It's going to read it in one sector at a time, and it's going to put it into a special directory buff that's inside the BIOS specifically for the directory use by the BIOS. It's just part of the alteration guide says put a buffer somewhere, and that's where mine ended up. Now, remember when it goes into the BIOS read routine, I printed this out. This is the standard debug, right? Disk 0, track 20, sector 0. That's the beginning of the directory. Then we added this to make sure all my code works okay. If I'm in track 20 and I want to know what slot I'm in, remember the answer is throw anything away that's not part of the least significant 8 bits. I think we're good, all right? This is not definitive because it's actually the same value, but it is because we just simply set H to 0 and we returned. What bank is that in? Now, is bank 0 right? Well, remember the bank comes from the most significant 2 bits of this nibble. And a binary 2 is 0010. Therefore, the most significant 2 bits are both zeros. Therefore, the bank has to be 0. So that jives. What about this address over here? The address comes from all the bits in here, because that's the slot number, or more specifically, the address here is the slot number. We have to shift it left once and throw away 2 of the bits, and then add these zeros over here, right? So what you're really going to do, if you think about it, you're going to multiply the slot number by 2, then throw away the most significant bit of this nibble and the least significant bit of that nibble right there. And since they're already zeros, what you really end up with is slot number basically times 2. Okay, and that's what happens quite often until the slot number gets bigger than 3, or 30, I should say. If you think about it in binary, this will always be just the slot number times 2 and then shifted left like that, okay? Until it's greater than whatever it is, 3F or something like that, okay? So these numbers all jive, and it also makes sense that when we're reading in the directory one sector at a time, it's going to read them in order. We talked about this before. They're always going to be on track 20, and it's going to read one sector, then the next one, then the next one, and so on. And each time we do this, because the track directly maps into our slot, every one of these is in the same slot, okay? That all makes sense. When we go to track 21 and then we read 4 sectors over there, we better be reading from slot number 21. Yes, we are. And the bank's still 0 because the bank number, remember, is the top 2 bits of this nibble here, which are still 0. And that's going to stay that way, now that I think about it, through the entire directory. Because the directory ends at 3F, we're going to see, on track number 3F. So the entire time we're scanning through the directory, we better see the bank number should always be 0, even as the slot goes up, because it's going to end around 3F, I believe. The address, every time we go to the next slot in our cache, remember the slots are 512 bytes each. So the first one was at 4,000 hex. The next one has to go up by 512 bytes. 512 in hex is 200. So when I go from 20 to 21, seeing this to go from 4,000 to 4,200 is exactly what we want. This is working perfectly so far. These positive tests look good. We should do some negative ones to make sure that it still works. As we see it go, slot number 27 is for E00, and then we go up to 5,000 in hex for slot 28. Does that make sense? 28 is the slot. The most significant 2 bits are still 0, and I said that we would see the bank stay at 0 until we get past 3F. So is 5,000 in hex twice 28? I would argue, yes, it is, because 28 times 2 in hex, right? Remember, the 2 is a 0010. Multiply that by 2 is shifting it left by 1, right? You end up with a 0100, which would be 4 if that's all there was in. but I got a 2.8. In binary, I got a 0010 followed by a 1,000. If you move this whole thing left by 1 bit, which is what happens when you multiply it by 2, the bit that's in the 8 moves over into this digit over here as the least significant bit there. Therefore, 2 times 2 is 4, plus the 1 from here is 5, and that's why this is 5,000 hex. Okay, you can work it out on paper if you don't believe me. And this should go on and keep going up by 200 in hex, 56, 58, 5A, as the slot numbers go up, and that's really nice. And then we get into the 30s for the slot number over here, and we see the numbers still go up 2 by 2 by 2 by 2 by 2 by 2 by 2, and we go all the way up to 3F, because just by pure coincidence, the directory happens to have exactly the right number of tracks in it, right? To go from 20 to 3F, right? Which is going to be what? 32 blocks. Is that right? Yes. And we can fit, I believe, 64 per bank. And therefore, it makes sense that since we started halfway through the first bank, and we're reading in a half a bank's worth of data in a direct mapped cache, we just burned through all the slots in order, starting from the middle of the first bank, bank number 0, to the end of bank 0. And our cache is working perfectly. It would have filled in all of those slots in this exact order. And this is a wonderful thing, provided that we don't end up needing to reuse those slots. The entire contents of the directory will stay in our cache, and this will be nice and efficient. And we'll see eventually the downside of direct map caches, because they're so well organized and they march through in order. Eventually, we'll find out that we'll start overriding it later on. It'll still be useful, but there may be better ways down the road. So if we do a directory command now that it's been booted, CPM's BDOS is smart enough to know at this point, remember, the whole point of doing this is to scan through to figure out what parts of the directory are actually used, okay, and which sectors on the disk are available if we want to create files and stuff like that, write things into them. In other words, it built that allocation vector. So, in other words, when I did the directory command just then, it's smart enough to know which tracks and sectors have directory entries in them, and it doesn't need to read any more than it's some minimal amount. So what does it do? It's going to go back and reread the beginning of the directory, and the only reason it's reading that one is because when we created the file system image, I talked about this before, the tools, for obvious reasons, because they're simplistic, fill the directory's entries in order from the beginning and on up as they go. In other words, this is not fragmented. So what is it going to do? It's going to read in the first one, which was, again, slot 20, bank 0, and put it into address 4000. And if we actually had a real cache at this point, it would be able to use the data that's already in the cache. But remember, all I'm doing is printing out where it would go if we finish our code. And then, of course, it's going to print out what it's going to do, and then it's going to go on and read another sector and print out the directory entries in each one of these sectors one at a time as it goes. And then what is it going to do? It's going to run down here. What's it doing down here? It reads in and it prints some stuff out. Then it wants to read another sector over here and print some more stuff out. Now, why do you suppose it didn't print 4 directory entries on that line like all of them did up here, right? Not that this is relevant, but it's just an interesting observation. Why would that be? The answer is because this file here probably has more than one extent in it. And it used up another directory entry that CPM is not going to waste our time saying, oh, adv.com used up 2 slots in the directory. We don't care. We just want to know that there's a file in there called adv.com. And then it moves on and says, okay, there's also something called advi.dat that uses apparently more than one slot in the directory as well, and then so on with pointer and dat and blah, 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 blah. This is avt.dat. So we got these files, and the reason that there's holes in our directory is because of files that consume more than one extent. Okay? All right. And one of the files in here is called readme. That's a small text file. Remember, there's a CPM command called type, which in Unix, this would just be cat. All right? Now, this is an interesting thing because if you think about it, the directory sits in the second 16K worth of data in our file system, in the disk partition, okay? And remember, when we're reading them all up here, it read in and put all the slots in, and it ends at 3F. This is the last slot number that's in bank 0 in our cache. So any data that represents the contents of any files anywhere on this disk must therefore be on a track greater than 3F, because you can't put data for files in the directory. And since the directory ends on 3F, readme must be in blocks on tracks greater than 3F. And this is interesting right now, because what we want to do is see if the slot numbers and banks and addresses work when the bank is not just 0. Because the 0 case is actually the easy one. When the bank is 0, we could be having bugs in our code that don't manifest themselves, because it's sort of like, adding 0, algebraically multiplying by 1 and adding 0. These identity cases and stuff like that can hide errant code, right? Can't hide from this one. So if I type out the README, what does it do? It says I need disk A, track 20, sector 0. It's reading the directory. It's reading 4 sectors of the directory. Why is it doing that? Well, it has to find it. Okay? It has to figure out where its data is. So it has to go back and reread the directory. So it probably found it in the 4th sector here and said, okay, fine. I now know where the data is. Now it goes and starts reading the data so it can print it out. Well, here's the text that it's going to print out. That's the README file that's in this particular distribution of CPM. Okay? So what did it do? It read in there. It figured out where the blocks are that comprise the value, the data bytes for that file. And then it goes and reads them. So we're on drive A, track number E4, sector 0. Notice the DMA now changes from F698 to 80. Remember that DMA buffer address 80 is the default I/O buffer that CPM likes to use, and that your TPA programs are free to use as well, just for general purpose I/O buffer. Just coincidental that that's where it decides to store this while it's doing its task. So what do we do there? We know the slot's E4 because that's just throw away the top half of the track number. We'll have to get the track numbers over, FF before we know for sure that happened, but that's pretty trivial code. I'm pretty confident that that's okay. So what bank is it in? So we've now moved over to bank 30. Is 30 the right bank for E4? I believe the answer is yes, because remember the bank number is the top 2 bits of this nibble and then shifted right twice. So E is 111 and then a 0. So the top 2 bits in this nibble are both 1s. If I take those 2 1s out and I move them to the right 2 bit positions and 0 everything else out, that's a 3. In fact, it's a 30. So that's exactly what we should have for track number E4. Now, what about this address? Well, remember, the address comes directly from the slot as well. We throw away the top 2 bits from the bank, and then we shift it left 1 bit, and then we add these 2 zeros over here. So what does that come out to? Well, E4, if you throw away the top 2 bits, is a 2-4. And then we have to shift it left once, which is multiplying it by 2. So 2-4 and hex times 2 is 4-8. and then we append the 2 zeros, so that worked perfectly. And with this trivial test, we can argue poorly. Therefore, it's perfect. Nothing bad gonna happen here, right? No, we've exhaustively tested it. Ugh, yeah, maybe. So our first task is done. Figure out where the heck the thing is supposed to be and code up some routines to give us those values. The rest of this then is a matter of, rather than using this block down here at the bottom of this file, we want to instead change the bank number and store the data in the address calculated for the given slot. So when we do the read routine next, so far so good. The debugging routines look good. The values look like they're probably okay. What do we want to do after that? We want to read the actual disk. We're going to, for the most part, still need this code. But down here, when it says, oh, I want to see if the SD card is in the buffer and so on, this is where our new cache logic goes. For the most part, selecting the RAM bank and stuff like that. Then there's some debug. Then what do? If we decide we're going to actually read from the SD card, we're going to remember what track, which SD block, we read in last, because we use our little one slot buffer as a kind of a cache. And this is the equivalent of our tag table that we need to deal with. Instead of having only one slot in one place to store and remember, oh, what's in that slot, we have 256 slots. So we have to figure out, which, where we're going to store this, because we don't have a single thing. Now we got a whole array of things. And that's not too bad, because we simply have a table somewhere and use the slot number as the index. And then we will simply store in there the most significant byte. We don't need to store the whole thing in there. For a direct map cache, as I mentioned before, the tags are really what we need to store is, at this point, is what is in the H register. The stuff, the bits that comprise the track number that we need to remember, right, that are not simply the slot number, right? The slot number is implied by which element in the table we store the H in, okay? So this is not too bad. Again, this is all because it's direct map. It turns out the code's super simple, very simple-minded type of thing here. But what the point is, we have n slots, therefore we have to have a table of n storage areas, the tags, right? And we also have to mark whether or not each one of our slots is valid or invalid. So we have 256 tags and 256 valid flags. I'll store that in the same table with the tags, by the way. And then we go on down here, and for the most part down here it would be the same, I think. And when we are all done and we say, I've got the slot that I need, where do I get the sector out of that slot? This logic is the same thing, because we've got to find one of the 4 128-byte sectors out of the 512-byte slot. I talked about this last time. Same thing, but it'll apply not to the one single buffer, one single slot. It'll be for the whatever slot that we put it in. What are we doing here? This is, and what I just said applies to this variable right here. That's the address of the one single slot. In our new code, this has to be the address that comes from, and is printed out in the debug routine up here, that comes from this address right there. Okay? So in the single slot, we have one address, which is the address of the slot, which is here. And in the new code, this will have to get the address from the S2A function. Okay, then this will work. And then we copy it to where it's got to go. Now this gets interesting. We may not be able to just do this, okay? Because remember, at this point, the data is in a slot that's in a memory bank that by definition is not in the in the TPA. What if we want to copy the data into like address 80 in that standard IO buffer that we actually saw working when I typed out the README file? How does it get there? Because the memory at address 80, which is down in this IO buffer right here in the memory map, is in this case it would be in bank 14, but it would be in a bank that's not one of the banks with all the SD cache. So let's say we stuck it in bank 2 for whatever reason, and we wanted to copy something out of here that happens to be in this bank into the other bank, which would be 14 in the new code, because maybe I want to copy it into this IO buffer or into some other thing that's part of the TPA. Okay? How do I do that? I can't copy from here to there. What I can do is copy from bank 2 up into here. So all those times when they want to read the directory and it goes to that F4 whatever address, those great big numbers, the F698, I believe, when the thing was scrolling by earlier, I can do that, but I can't do it over to here. So what I'm going to do is I'm going to create a special buffer up here that has hex 80 bytes, 128 in decimal. What's commonly called a bounce buffer. Okay? If I need to move it from one bank to another bank down here, it cannot happen directly. Therefore, I have to read it, copy it up to here. I'll put a private buffer in the BIOS specifically for this purpose. And then when that's done, I'll switch the bank to wherever the target is, which would be 14, presumably. And then I'll copy it from the bounce buffer back into the target bank. All right? Simple, stupid, easy. There's other ways to do this sort of thing, like copy a bunch of bytes out of here into many registers in the Z80, including like the alternate registers if you want to. Then switch the banks, and then copy the registers all into this bank, and then switch the bank back again, load up a bunch more registers, switch the bank over here, store them back out. You can do things like that, but you'd have to add up the timing and find out if it is any faster than just LDIR up to here, switch the banks, and then LDIR back down. I think I did a back of the envelope of that at one point and figured that it would actually take longer without the bounce buffer if I was just using a bunch of registers. Just because of the time it takes to fetch all those instructions and stuff like that. And you'd have to write loops and all this other stuff. So, yeah, if you're really good, let me know. Do the math. Comments below. This thing already runs slow enough. It'd be nice to optimize that. If there's a better way than just a pair of LDIRs, okay? So anyway, that's the point of what would have to happen in this area, okay? And then we have the stack foolishness down here. Now, remember what happened with the stack. Now, this is actually kind of a big deal. A bigger deal than it even was before. We switched to a local stack that's just a buffer at the end of the BIOS, right? Because when we call, if and when we call the SD routines down here, we need a lot of stack space. We're storing 32-bit values, plus this thing uses the stack, plus our debugging uses the stack. There's a lot of stack stuff going on. So I had to make room for a bigger stack while this code runs than what was available to us with the default stack that's given by the BIOS. Now, we have another reason to concern ourselves with the stack and where the stack is. Buried in the alteration guide somewhere, it does talk about the fact that if the BIOS calls the BIOS routines, you get whatever it was, like an 8-level stack or something like that. And that's not a very big stack. Now, the one that I put in my BIOS that we use for this purpose is down here, and that's got 64 bytes, which is a 32-level stack, okay, which is notably more than 8 or 7 or whatever that was. So we have a little more elbow room, okay? But the thing is, even though the BIOS says that you get a stack that has a couple of levels, and odds are that that stack comes from some memory that's probably inside the BIOS. By that I mean memory that's in this green area up here, in the high part of memory, over 8,000. The alteration guide doesn't state that it must be. And what if you have a special utility app that directly calls into the BIOS, because it can, it's there, okay? And what if they make a call into the BIOS while the stack is down here? And the BIOS decides, okay, I'm going to switch over to bank 2 and start diddling around over here. And while I'm diddling around, I need to call a subroutine. Well, the stack pointer will be pointing at an address that's right in the middle of bank 2 and start clobbering what's in bank 2 here. So now there's two reasons that we care about the stack and where it is for sure before we do anything with the memory banks. Now it is super duper mandatory that we switch over to a local stack, and it's mandatory that that stack absolutely is in the northern half of the address range, okay? Which by definition it's in, because that label is part of the BIOS, okay? I could probably add a comment into retro.asm that reminds my future self that that must be in the high bank. Otherwise, all hell's going to break loose elsewhere, okay? So that's one thing we need to make real sure. You do not touch the banks until down here after you've swapped the stack and got ready, okay? So, in other words, we're not going to just get all these values, set it all up, and then fall into this code down here. We're already dead if we do it that way. What we're going to do is fix the stack, then mess with the memory banks, then use the memory banks and figure out where everything's going to go. Then we're going to do our data transfer. In this case, it's the read routine. So if we don't already have what we want, when we run this code here, it's going to be reading the SD block into the target buffer. In this case, it's in the DE register. Instead of just putting the 1 in there, we're going to put in the address from the subroutine that we saw earlier. Okay, then we call this one. It'll copy it into the slot in our cache, and then we'll put the bounce buffer logic down here. Okay, clean up our stack, and we're done. All right, that's what we're going to do. Now, it turns out this is pretty straightforward, because we actually have everything we already need. We got the block number, the bank number, the slot, everything else all ready to go, except for one thing. Where's Columbo when I need him? There's just one more thing. Where does the tag table go? Well, our tag table right now is only 256 bytes. We could just stick it in the BIOS if we wanted to. And after all, right now, or shall we say yesterday, right, that SD block buffer in there is 512 bytes in size. So that's already double the size of our tag table, okay? But we also need to have our bounce buffer in there for the, the 128 bytes. So we're still ahead of the game, right? But as we tinker around with our design for our cache, the tag table is going to grow, right? The size of the tag table is proportional to the number of slots. And right now, I'm only using 4 of these 13 banks. I'd like to be able to use more. Therefore, that tag table is going to grow. It'll also most likely double in size if we ever use a design for an associative cache rather than a direct map cache. Because part of what's going to happen, as you will see when we go to an associative cache, is there's more information to keep track of. So then it'll grow. I mean, it could be on the order of a K at that point. So this thing could consume more state information to keep track of what we're doing. So what I'm going to do for the tag table up front is I'm going to store it in a bank on its own right. So what we're going to have is bank 15 for the high RAM, bank 14 for the low RAM when CPM is running for the TPA and the IO buffer and all that. It's going to go into 14. 13 is going to be a data state bank where we're going to, on day 1, all I really need to put in there is the tag table. And then the remaining banks are free for us to use to hold all our cache slots. All right. So let's put some notes in here. So bank F equals, high RAM. Bank E equals low CPM RAM. I should put this, and now that what am I thinking? I should put it in here. Well, as I said before, it doesn't even really belong in here. What I'm going to do is I'm going to copy this into the other file. And the reason it doesn't belong in retro.asm, formally, it belongs here because when we do an associative cache, the mapping may work differently than we do other ones. These two here are not going to be negotiable. These two, as you saw before, and as you know, are put here by the BIOS. The banks, 0 through D are ours to play with. All right, so what I'll do is I'll put an asterisk in here to remind us all. Oops. Well, I guess these are footnotes, so they would go over here, right? Let me say it like this. Say these banks are controlled by the BIOS. Okay. And then these other ones are going to be whatever we want to do in here. So this is going to be where our tag table goes. Alrighty. Well, this is all wonky. Must have proper indentation. Okay. Oh, it's because I copied and pasted it. Okay. Let's make a pretty box. Gotta have a pretty box. And keep the extra blank. 15 minutes later, box formatting. All right, so this is going to be our, let's call this the direct map DM cache tag table. Because who knows, when we might have some other data. Maybe the tag table will be more than one bank. I hope not. That's 32K right there for a tag table. Seems a bit much. All right, so this is going to be where everything goes. If I look at the clock on the wall, we're getting a little late. So, okay, first pass here. We got the values that we want. The plan is set up the stack in high RAM before we pull the rug out from under our feet, and then use these values here instead of the hard-coded ones there. So next time, we'll work out the code that goes, that'll scattered around down here to deal with the multiple slots, the 256 slots in our bigger cache rather than the one that we have now. All right? So I'll see you then. Thanks for watching.